Well, welcome everyone. My name is Heidi Buffington, Director of Admissions here at St. Louis University's Madrid, Spain campus. I have the pleasure of introducing the talk that we have today that's part of a series called Viral Thinking. This is being recorded on July 10th, so the information may have changed when you're watching this. In the Viral Thinking series, we'll share information across several disciplines and how they've been affected by the corona crisis. It's our hope that the talks spark further conversations that are relevant and thought-provoking. Much like a viral YouTube video, our hope is that the conversations inspired in the series will catch on and go viral, so to speak. Much like the liberal arts education style, where students study many disciplines that are ultimately interrelated, so is the coronavirus crisis. While COVID-19 at first look is a biological subject, and we do have a talk on that, at the same time, the coronavirus crisis is affecting many areas like the economy, people's physical and mental health, office and human resource management, world health policies, and business models. In fact, our political science department will be offering an online course this fall about the COVID crisis, and we'll cover topics such as the political communication strategies, how political leaders react to uncertainty, and how political systems manage crisis. Maybe you didn't have the virus or suffer from COVID-19, but inevitably you will be affected in some way, shape, or form. Today, we'll be talking about math. I tested positive for a disease. To know if I'm really sick, do I need to know about the quality of the test, or is there any other relevant information I should worry about? What does the quality of the test even mean? For the same test, is a false positive in New York as likely as a false positive in New Zealand? This talk will be given by Drs. Ana Portilla and Ana Granados. So let me introduce them. Dr. Ana Portilla earned her master's in mathematics from the Universidad Complutense de Madrid. After earning her degree, she started working as a systems analyst in research and design at a computer company. Then she decided to go on to get her doctorate in mathematics from the Universidad Carlos III de Madrid with a specialty in complex analysis and geometric function theory. She's also the co-author of nearly 30 research papers and a textbook. She's also participated in a number of internationally recognized research projects. Dr. Portilla has been a professor at St. Louis University Madrid since 2006. Welcome. And we have Dr. Ana Granados. Dr. Ana Granados got her master's as well as her doctorate from the Universidad Autónoma de Madrid with a specialization in the areas of complex analysis and geometric function theory. She did a first postdoctoral fellowship at the University of Washington in Seattle with a Fulbright scholarship, and a second one in British Columbia, Vancouver. She's the co-author of some 20 research papers in her area of expertise. She's also been a member of numerous internationally recognized research projects. Dr. Granados has started several different projects that get secondary students interested in maths for more than 10 years. She's been a professor in the project called Estímulo del Talento Matemático in Madrid, which is roughly translated as Stimulating Mathematical Talent. Dr. Granados has been a professor at SLU Madrid since 2007. And both Dr. Granados and Dr. Portilla for many years have dedicated part of their time to outreach activities on math directed to high school students and the general public. They are two of the three founders of a science outreach association called Science a Banda, which takes place in a local restaurant specializing in rice dishes. A banda is a play on words because it's a type of rice dish. And actually, Science a Banda was created in the spirit of the International Pint of Science Festival. The Pint of Science aims to communicate contemporary scientific developments to the public by bringing scientists to pubs, cafes, and other public places. So without further ado, I'm going to pass it over to Drs. Granados and Portilla.
It is with great regret that we inform you on your positive XY antibody test result. Dr. Strangelove.
Oh, Marianne. Dearest. But did they tell you what the positive predictive value was? Any other information? It is important to know the prevalence of the illness.
What do you mean?
I thought you had some kind of understanding.
No. I don't know as much as you think.
Haven't you heard about sensitivity?
Yes. No, I didn't study enough maths. I always thought it was useless, that it would never apply to the real world. What did I do?
But look, this might be a false positive.
Are you sure? Are you sure? Oh my God, I wish I knew more maths.
I'll explain you the math, no worries.
Precision, reliability, sensitivity, specificity. We have a clear idea of what these words mean in everyday conversations, but lately they appear frequently related to the quality of different diagnostic tests. And maybe, in this specialized context, the meaning is not what we think it is, especially since they often come to us after going through the unskilled press sieve, resulting in a kind of cross-contamination between ordinary and scientific language. But in science, it is very important to give precise definitions of the terms used. It is essential that we agree on what we mean when we use certain words. We have two different objectives for this talk. The first one is to clarify the meaning of these terms in the statistical context. More specifically, if we use them to quantify how good a diagnostic test is, do they mean what we think they mean? Or are we putting very different concepts under the same umbrella?
And the second goal? Lately, we hear much talk in the media or social network about the large number of false positive or negatives that certain diagnostic tests give. And from this, a low quality of the tests is automatically inferred. But is it really so? Or are there any other things with the relevant role besides the intrinsic quality of the test? Is it possible to have tests with more than acceptable quality parameters that, however, produce many false positive or negative? In short, and for practical purposes, I have received a positive diagnosis in a test. Should I be concerned? How much should I be? What information should I ask my doctor that will actually be more relevant to my peace of mind than the intrinsic quality of the test? What is the first idea that one could think of to measure the quality of a test? Perhaps to quantify its successes? That is, when the test is applied to a population, in what percentage of occasions does the diagnosis it provides reflect reality? I mean, what is the percentage of occasions in which it gives positive when applied to a sick person and negative when applied to a healthy one? Suppose that there is a test that, regardless of whether it's applied to a healthy or a sick person, always gives negative. If you had to put a quality label on this test, the most appropriate would be this. Well, no, better this one. It's a scam, no matter how you look at it. Suppose now that there is a population in which the prevalence for a certain disease is 5%. It means that 5% of the population have the disease and 95% are healthy. Now we are going to apply our scam test to this population. What are the results? Remember that our test gives always negative, no matter to whom it's applied. In this sample of 100 people, there are 5 people sick and 95 are healthy. So if we apply our test to this population, it will identify as healthy to 95% of them. And therefore, for these individuals, the diagnosis is correct. But it will give also a negative test to the 5 sick individuals. However, if we define the precision as the probability of getting the diagnosis right, this test is accurate, that is, it diagnoses correctly 95% of the times. It's true that it's not its merit. It is that the disease is not very frequent. When there is a lot of imbalance between the healthy and sick groups, this concept of precision of the test doesn't seem very useful. We really need to find another strategy to quantify the quality of a test. The strategy, the idea applied today, was designed in 1947 and it's still in force. It consists of something as simple as reading. Separating sick from healthy individuals and evaluating how well the test works in each of these two groups separately. That is, the precision is not calculated globally, but in each group.
Following this idea, we separate and complete each group so that there is a significant sample of individuals in both. How is the distinction made between healthy and sick? What is usually done is to use another existing and validated test. That test is the one taken as a reference. Why do we evaluate a test if there is already another one that works well? What generally happens is that this reference test is a sophisticated, invasive, or expensive method, while the test being evaluated is proposed precisely as an alternative that can be applied under conditions of time or resource shortage. Okay, so we ran the test among the healthy people. In this case, as you can see, out of the 100 healthy people, it identified correctly 95 of them. The specificity indicates the ability of this test to identify those who are actually healthy. In this case, the specificity would be 95%. Here you can read a P, a parenthesis, and then a vertical bar between the minus and the phase. How this is read is, what is the probability that if the person is healthy, then the result of the test is negative. In the same way, the sensitivity is going to indicate the ability of the test to detect a sick subject. That is, it measures how sensitive the test is to the presence of the disease. In this case, among these 100 sick individuals, the test identified correctly 90 of them. Okay, so we would say that the sensitivity is 90%. The probability that if the person is sick, the test will give a positive result is 90%. This particular test seems to be a 5-star test. It has a high sensitivity and a high specificity. It will be very useful to assess the health of the population. Or maybe not. We will return to this question later.
If we apply now these concepts to our scam test, what happens? Well, remember that it always gives negative, so it identifies correctly as healthy 100% of the healthy individuals. The specificity of our test is 100%, that's good. But what happens in the group of sick people? Well, our test also identifies as healthy 100% of them. It means that it's wrong in 100% of the occasions. The sensitivity is 0%. It's not able to identify even one of the sick people. This test has been proved to be more than useless. So these are the labels that our test deserves. In order to have a high-quality test, both parameters, sensitivity and specificity, both of them must have reasonable values. It's not enough if one of them is very good, like specificity in this case, when the other one is awful. So we have an acceptable way to measure the quality of a test, specificity and sensitivity. And this is great, both to do epidemiological studies at large population scale and also to compare the quality of two or more different tests. However, to me, as an individual, or to my doctor when he or she has to decide about giving me further tests or treatment, these values are not the most relevant ones. So if I have received a positive diagnosis in a test, when should I worry? And how much should I worry?
Remember that the sensitivity is the probability that if I am sick, I will get a positive result. But what I, as a patient, want to know is what is the probability that if I test positive, I will be sick. It is so important, so useful both for the patient and the doctor that we have given it a name in math. Positive predictive value. It is similar to sensitivity, but in reality it is very different. The roles of which is known and what one wants to know are reversed. The question is there a tool that allows me to cross the wall?
To cook a Spanish omelette, tortilla de patatas, it's not enough to have potatoes. Other ingredients like eggs and onions are also needed. And we need too an energy source. Similarly, to cook the positive predictive value from the sensitivity, we need other ingredients like specificity, that together with sensitivity are the intrinsic parameters that measure the quality of the test, but also we need something that has nothing to do with the test itself, but it has to do with the population to whom it's going to be applied, and it's the prevalence. We really need to know how frequent the disease is in the population in which it's going to be applied. And we need an energy source, and the energy source is Bayes' theorem. But Bayes' theorem is much more than an energy source because it's magic. It lets you go in both directions, from sensitivity to the positive predictive value, but also from the positive predictive value to sensitivity. It's a two-way highway. Well, Bayes' theorem, let's say that allows uncooking the tortilla and separate the potatoes from the eggs. And you can also cook the negative predictive value from the specificity. So let's see all this in action. We have a test with a sensitivity of 90% and an specificity of 95%. It sounds quite solid, right? Now, if you test positive, does it mean that you are sick with a probability of 90%? 95%? Something in between? Let's see.
We ran this test in 3 different populations. In each one of them, the prevalence is different: 5%, 1%, and 20%. In the first population, almost 49% of the sick population is identified correctly by this test, but 51.4% will get a false positive. That is, they will receive a positive test while being healthy. In the same way, one can calculate that the negative predictive value is 99.4%, so it identifies very well healthy people. When prevalence is 1%, please notice that the number of people who will receive a false positive is 84.6%. Again, this test is going to identify healthy people extremely well because the negative predictive value is 99.9%. When the prevalence is 20%, the number of false positives decreases very much. Different prevalence has a big effect in false positives. Consider a second test. The sensitivity and the specificity of these tests are both 99%. Still, if we have very low prevalence, false positive arise highly, while it identifies very well healthy people.
In conclusion, if you test positive for a certain disease, should you be concerned? Well, our advice is that before worrying, ask your doctor for the positive predictive value of the test. And if the test gives you negative, can you rejoice? Yeah, why not? Come on, rejoice. There will be plenty of time to be sorrowful later. But if you like being uninformed optimistic, then ask your doctor for the negative predictive value of the test. Positive predictive value and negative predictive value give the probability of suffering or not from a disease once the result of the diagnostic test is known. They encapsulate not only the quality of the test itself, given by the specificity and sensitivity, but also the prevalence of the disease. They serve to measure the relevance of the theoretical values of sensitivity and specificity in a particular population with a certain proportion of sick people. Like sensitivity and specificity, they can be written as conditional probabilities, turning around what we know and what we want to know. They are the true post-diagnosis tools that help doctors and patients make decisions, like repeating the test, try a more invasive diagnostic method, or wait for new symptoms.
If you are one of those who wants to know what is included in the exam, here is the cheat sheet. If you have been tested, remember that positive predictive value and negative predictive value measure how much the test is correct. But of course, if we know how much it hits, we also know how much it fails. Suppose you have a 100 millimeter beaker. Suppose you're given a negative result. The false negative will be the complement to 100 millimeters negative predictive value. The false positive will be the complement to positive predictive value.
Now I'll know what to ask if I were to get a positive COVID test result. And thanks to everyone who was watching. With so many types of tests available and coming out in the market, if you want to know more about the types of tests available and testing in general, we do have another video in the series, in the Viral Thinking series, that you can see on YouTube. And thanks again for tuning in.